Okay, this video is going to continue with chapter 6, section 3, vectors. This would be day 2 or part 2 of those notes. So we're continuing on with yesterday where we learned what a vector was, how to find component form and magnitude. And so we pick up with writing a vector in terms of its magnitude and direction. So this says let V be a non-zero vector. If theta is the direction angle measured from the positive x-axis to V, then the vector can be expressed in terms of its magnitude and direction as, and here's the formula. So basically what you're going to be given here is the actual angle of theta, the value there, and then you're going to get given the magnitude of the vector. And what you want to try to see is if you were to able actually to measure the theta and the length here, what would be the component form of this ray? And you can write it in either component form, this vector, I don't know why I said. You can either write it in terms of ij or you can write it in component form. What you're going to do to find, and this can also be broken up, this is the horizontal component or the horizontal change. And if you look at this equation, it says take the magnitude and multiply it times the cosine of theta. So that should make sense because cosine is the x value. And then the second part of this would be the vertical component or the vertical change. And that is the magnitude times the sine of theta. So sine would be the y value. Again, hopefully that makes sense. You can write this 3 ways actually. One is in component form. So this would be the magnitude times the cosine of theta and then the magnitude times the sine of theta written in your vector form. Or it could be written with your ij. So it would be the component form times the cosine of theta I plus the component form, plus the magnitude of the vector times the sine of theta j. Or in one question, it even will just ask you directly what's the horizontal difference or the horizontal component, horizontal change, something like that, and then the vertical. So you would separate them out where the horizontal is the magnitude times the cosine and the vertical is the magnitude times the sine. So example 6 says find the component form of V given its magnitude and the angle it makes with the positive x-axis and then sketch V. So the magnitude of V is 2 square root 3 and theta is 45 degrees. So if I could picture this, 45 degrees and 2.3 or 2 square root 3 is the length of this vector. So I'm going to find it using the equation or the little formula we just talked about, which is the magnitude of V or 2 square root 3 times the cosine of theta, which would be 45. And it says component form. So I'm going to put it comma 2 square root 3 times the sine of 45. I know 45 degrees has the coordinate point root 2 over 2 and root 2 over 2. So the cosine is square root 2 over 2 and the sine is square root 2 over 2. And then we simplify these. 2's cancel and square root 3 times square root 2 is square root 6. And we cancel these and square root 3 times square root 2 is square root 6. So the component form would just be root 6 comma root 6. If it wanted it in ij form, root 6i plus root 6j. Both of those would be right. Then it says sketch V. So I know to be just like this. I want it to be from 0, 0. So then on my x-axis, I would go right square root 6, which is in between square root 4 and square root 9, or in between 2 and 3. We're going to say like 2 point, I don't know, it's closer to 6 than it is 4, but maybe like a 2.3. I'm sorry, it's closer to 4 than it is 9. So maybe like closer to 2 than 3, maybe like a 2.3. So I'm going to go to the right, 1, 2, a little ways, and then up 1, 2, a little ways. I'm going to plot that point, and then I'm going to draw vector V. Example 7 says a ball is thrown with an initial velocity of 70 feet per second at an angle of 40 degrees with the horizontal. Find the vertical and horizontal components of the velocity. So they even give you a little picture here. You're seeing that this would be your vector. Your 70 feet per second is your magnitude, and the 40 is your theta. So if I want to find the vertical component, I'm using sine. Vertical would be the magnitude of this vector times the sine of theta. So in this case, it's 70 sine of 40 degrees. And the horizontal component is cosine, so it's the magnitude times the cosine of theta. So in this case, 70 times the cosine of 40. And these are not unit circle angles, so we're going to use our calculators here. 70 sine of 40 is 44.995, so this is going to bump everything, and this becomes 45.0, and its distance here would be feet. And then 70 cosine of 40 is 53.62, and again, this would be feet. Example 8 says to find the component form of the sum of u and v with directional angles theta u and theta v. And so there's a hint here. We're going to find the component form separately, and then we're going to add the vectors. So in order to find the resultant, which a lot of times you'll see that like a resultant vector, this means the sum of these vectors. What we have to do first is find the component form of each of these vectors, and then we're going to add them together. So first I'm going to find, would be vector u. So the component form of u would be 5 times the cosine of 0 degrees, comma 5 times the sine of 0 degrees. And we know at 0, our coordinate point there is 1, 0, so the cosine is 1. And the sine is 0. This component form would be 5, 0. Then we're going to find the component form of v. My magnitude's 5. My directional angle is 90 degrees. So I'm going to do 5 times the cosine of 90 and 5 times the sine of 90. And at 90 degrees, our coordinate point's 0, 1. So the cosine is 0 and the sine is 1. So 0, 5 is the component form of v. So this is u, this is v. If I want to add the two together, I simply add the x's and the y's, and I get a resultant magnitude or resultant component form of 5, 5. Now, if you had drawn this, if you actually had labeled this and it was able to be, this time it is because it's 0 and 90 degrees, it would be easier to measure this because those are angles we can draw without a protractor or anything like that. I would have gone at 0 degrees, 1, 2, 3, 4, 5. That would be u. And then at 90 degrees, 1, 2, 3, 4, 5. That would be v. So if I wanted to find the sum of these, I could find it here, which makes sense that that would be 5, 5. Not all those angles would be able to be drawn accurately without a protractor, which is why you would need to know this formula. Or when you see stuff like this. So this is going to ask for the angle and magnitude of the resultant vector given two either vectors or forces. So to find this, if you have, it's a lot of times like you're just talking about one force is pushing this direction, one force is pushing this direction, then what we're going to do is we're going to use the angle and magnitude that's given, kind of like what we just did, to find the component form. So we're going to find the magnitude times the cosine of theta and the magnitude of the times the cosine of theta of each of them, like we just did. We're going to add them together, and that's where we ended the last time. We actually just found the component form and we were done. Now we're going to take it a step further, and we're going to find the magnitude of this sum and find the angle of the resultant vector. So to find the angle, we say the tangent of an angle is equal to sine over cosine, which would be the change in y over the change in x. So what we get here, we're going to put over what we get here. And then we're going to inverse tangent that whole thing. So we're going to walk through that process a couple of times. Here's what it's going to look like. It says graph the vectors, and actually we've already graphed this. I graphed this for you. So you're just going to find the resultant vector. and then find the magnitude and direction of the resultant vector. So if we extend out from the ends of both of these parallel to the other side, I should have gone a little bit further, but it looks something like this. This would go here. And then from here to my vertex, that's going to be the resultant vector. Now I need to find the magnitude and the direction of this. So I'm going to find the component form of each of these vectors. Then I'm going to add them together. Then I'm going to find the magnitude and the theta based on that. So I'm going to start with the 300 one. 300 has the angle 70. So it would be 300 times the cosine of 70 and 300 times the sine of 70. That's not a unit circle angle, so I'm going to let the calculator do the work. 300 cosine 70 is 102.606, so 61. 300 times the sine of 70 is 281.9077, so we're going to say 908. That's the component form. If I gave this a name, this would be U. Then I'm going to find the component form of the pink line here, where my magnitude is 40, so we're going to call that V. My magnitude is, not 40, 400 times the cosine of 25 degrees, and then 400 times the sine of 25 degrees. 400 cosine 25 is 362.52, and 400 times the sine of 25 is 169.05. That's the component form of V. So to find the component form of the resultant vector, we add these together. So I'm going to add the two change in x's, 102.61 plus 362.52. So 102.61 plus 362.52. And then I'm going to add the two y's, 281.908 and 169.05. And the 102.61 plus 362.52 is 465.13. 281.908. I don't know why I went 3 decimal places on that. That should have just been 91. Plus 169.05. And I get 450.96. So that's the component form of U plus V, or the resultant vector. But now I got to go 2 steps further. One is to find the magnitude, and to find the magnitude given the component form, we're going to do the square root of the change in x, which would be 465.13 squared, plus the change in y, 450.96 squared. Let the calculator do that whole thing for you. 465.13 squared plus 450.96 squared. And I get 647.85. This would be the magnitude of U plus V, the resultant vector. Then I want to find the direction of the result, and that means whatever theta is. So the tan of theta is equal to the change in y, 450.96, over the change in x, 465.13. And then we tan -1 because we want the angle. So I inverse tan 450.96 divided by 465.13. And theta is 44.11 degrees. So it's a long process, but it's the same process every time. If I have 2 vectors and I want to find the magnitude, first we found the component form of the resultant vector. So we just did the individual component forms and then added them. Then we wanted to find the magnitude, so we take that component form, we square root the a squared plus b squared. Then we want to find the theta, so we do tan of theta equals the change in y over the change in x, and then inverse tangent that to get the actual angle measurement. Okay, we're going to do it one more time. This time we're actually going to draw this out. So this says two forces, F1 and F2, of magnitude 5 pounds and 12 pounds, respectively, act on an object. The direction of F1 is north, 20 degrees east, and the direction of F2 is north, 75 degrees east. Find the magnitude and the direction of the resultant force and express the magnitude to the nearest hundredth and the directional angle to the nearest tenth. So what the heck does this even look like, right? So we're going to start with, I'm just going to draw an axis for us to start drawing this out on. And I'm going to say force 1, we're going to do in the lighter pink. And force 2, we're going to do in a lighter green or lighter teal, lighter blue. So force 1 is going north 20 degrees east. So I would go north and then east to the right. That's going to be 20 degrees, and that's going to be force 1. Then I go to force 2, and force 2 is north 75 degrees east. So north again, but this time 75 degrees east. This is obviously not accurate. That would be 75 degrees, and that's F2. So in order to find the resultant vector, I have to find the component form of each of these. And to do that, I have to know the angles inside these angles. So from the x-axis up, what I have is from the y-axis down because I have the bearings. So instead of using 75 as my theta, I'm going to use 90 minus 75, or 15 for F2. And instead of using 20 for F1, I'm going to use 70 because, again, that would be the complement to 20, and that's what's inside. Now, F1 has a magnitude of 5 pounds, and F2 has a magnitude of 12 pounds. So the first thing we're going to find is component form. F1 would be 5 times the cosine of 70, and 5 times the sine of 70. And then I'm going to go back and do that calculator work in a second. But I'm going to set up F2, 12 times the cosine of 15, 12 times the sine of 15. And now we let the calculator again do the work for us. So 5 cosine 70, 1.71, 5 sine 70, 4.698. So that's going to be 4.70. Component form of F1. Now F2, 12 cosine 15, 11.59, 12 sine 15, 3.105, so 11. Component form of F2. Now to find the component form of the sum of these, we're going to add together 1.71 plus 11.59, the two x changes, 13.3. And then we're going to add together the two y's, 4.7 plus 3.11, 7.81. And this is the component form of F1 plus F2. Now to find the magnitude of those, magnitude of F1 plus F2, I'm going to do the square root of 13.3 squared plus 7.81 squared. And I get the magnitude is 15 point, it says magnitude round to nearest hundredth, 423. So 15.42. And the directional angle, the tan of theta, equals the change in y, 7.81, over the change in x, 13.3. And I'm going to inverse tan that. So second tan 7.81 divided by 13.3. And I get theta is 30.4, and this time around to the nearest 10th degrees. So if I had actually done my diagram accurately, I would be able to estimate this. This would be 30 degrees, which obviously would be somewhere over here, and 15 is obviously going to pass the 12, which, again, if I had done it accurately, I could get by diagonally drawing these out. Where they intersect would be the resultant vector. All right, that wraps up 6-3. So please make sure you submit the notes just for these last 8 slides. And then use the remaining time to work on 6.3 part 2's homework. Have a great day, guys.